Hi, this is Dr. Gilbert Eyabi. Welcome to Abstract Algebra Lecture 1, Sets Part 1. In this series of lectures on abstract algebra, we would use the text elements of modern algebra. Let me start by saying that abstract algebra had its humble beginnings in attempts to address mathematical problems such as the solution of polynomial equations by radicals and geometric constructions using straight edge and compass. From the solutions of specific problems, general techniques evolved that could be used to solve problems of the same type, and treatments were generalized to deal with whole classes of problems rather than individual ones. We start our study of abstract algebra in Lecture 1 with the concept of sets. Before proceeding, I should make mention that abstract algebra is all about proofs, and we would start that from the very first lecture. We assume that students taking this class must have already taken at least one basic introduction to proofs class. So I'm going to go right ahead and start off with the concept of sets and introduce proofs from this very first lecture. Section 1.1, Sets. Let's start with the definition. A set is seen as a collection of objects about which it is possible to determine whether or not a particular object is a member of that set. That is very important. If I give you an element or an object, can we say for sure whether that element is a member of the set or not? Sets are usually denoted by capital letters A, B, C, X, Y, and so on and so forth. Members or elements of a set are usually denoted by lowercase letters, such as So elements or members of a set are usually denoted by lowercase letters A, B, C, X, Y, and so on and so forth. There are two major representations of sets: the roster notation and the set builder notation. In the roster notation, we list out the elements of the set completely, or we use an ellipsis. For example, we have the set A equals 0, 2, 4, 6, 8, 10. Or we could have the set B equals the set 0, 1, 2, 3, 4. The three dots are known as ellipses. The second method of set representation is known as the set builder notation. In the set builder notation, we use braces to enclose a property that is the qualification for membership. A property that is the qualification for membership in a set. In other words, an element belongs to that set if and only if it satisfies and fulfills the qualification for membership in that set. Example, let C be the set of all integers, set of all x in Z, that means element of Z, or that means element of the set of integers. So let C be the set of all integers such that x equals 3r minus 1 for some integer r. So C equals the set of all x in Z, set of all integers, such that x equals 3r minus 1, where r is an integer. Is 8 an element of C? In other words, can I find an integer r such that 8 can be written as 3r minus 1? Is that possible? And the answer is yes. 8 equals 3 times 3 minus 1. So 8 is an element of C. And we're good. Is 7 an element of C? Well, we can prove that it is or it's not exhaustively by inserting all the possible values of an integer in the place of r and checking if any of those would yield 7. Or we can do it by contradiction. So let's verify that together. Suppose there exists, that symbol means there exists. Suppose there exists an integer r such that 7 can be written as 3r minus 1. Then solving for r, we end up with r equals 8 over 3, which is not an integer. That is a contradiction right there. So what is our conclusion? 7 is not an element of C. I would personally use this symbol to mean contradiction. Subset. A set A is called a subset of another set B if and only if every element of A is an element of B. i.e., we say A is a subset of B if and only if for every x in A, x is in B. And that sign there means for every. How do we use this concept in proofs? You would be required very often to prove that one set is a subset of another set. So for example, if we want you to prove that A is a subset of B, this is how you proceed. You let x be an element of A. X arbitrary. Then show using definitions, axioms, properties that x is also an element of B. Example. Let C be defined as the set of all integers such that x equals 3r minus 1 for some integer r, and let D be defined as the set of all integers such that x equals 3t plus 2, where t is an integer. Prove that C is a subset of D. Proof. We are going to follow the proof technique very closely, and I want you to watch how we prove this because I would expect you to use it to solve subsequent problems. Let x be an element of C, so x fulfills the defining property of C. We must show that x is an element of D. It's very important to learn how to write this out nicely you don't know who's going to read your proof. So you want to make sure that whoever reads your proof understands what you're doing, where you're going, what you're trying to say. And I usually proceed with IE. Explain to the person what you really want to show. What is it that we're interested in? We want to show that X is an element of D. IE, I want to show that there exists an integer T such that X equals 3t plus 2. Okay. So that's where I'm going. I want to show that there exists an integer T such that X equals 3t plus 2. But what do I have in my pocket? But X, an element of C, what does that mean? It means that there exists an integer R such that X equals 3R minus 1. Okay, and that simply implies X equals 3R minus 1 minus 2 plus 2. Observe that I haven't really done anything. It's a trick we would perform very often in abstract algebra, and I need you to catch the trick. I subtracted 2 and added 2. Haven't done anything yet. I've done much. A little algebra, our old friend algebra. This becomes 3R minus 3 plus 2, which is 3 into R minus 1 plus 2, which is 3t plus 2, where t equals R minus 1. Remember, our goal was to find an integer t such that X equals 3t plus 2. Well, we have found a t, and X equals 3t plus 2. Are we done yet? No. I have to verify very clearly that t is an integer. Now, R is an integer. 1 is an integer. By properties of integers, remember I said you use definition, you use axioms, you use properties. By properties of integers, the difference or the sum of two integers is an integer. So if R is an integer, 1 is an integer, then R minus 1 is an integer. Now the proof is complete. I can then conclude that C is a subset of D. Done. Equality of sets. Two sets are said to be equal if and only if they contain exactly the same elements. Well, in abstract algebra, we would deal with sets mostly in the set builder notation, and therefore it would be almost impossible to list out all the elements in the various sets and then do a one-to-one mapping to verify that the elements are exactly the same. So how do we interpret this concept in terms of proofs? i.e., A equals B if and only if A is a subset of B and B is a subset of A. i.e., A equals B if and only if A is a subset of B and B is a subset of A. Example, let's C equals the set of all integers such that X equals 3R minus 1. We've seen this example before. And D is the set of all integers such that X equals 3t plus 2, T an integer. Prove that both sets are equal. Well, we already proved that C was a subset of D. All we have to do now is verify that D is a subset of C. So we want to show that D is a subset of C. Let X be an element of D. Must show that X is an element of C, i.e., there exists an integer such that x is 3r minus 1. But x in D, what does that mean? It implies there exists an integer t in Z such that x equals 3t plus 2. i.e. that means x equals 3t plus 2. Why don't I add 1 and subtract 1? And that will give me 3t plus 3 minus 1. And that will give me 3 into t plus 1 minus 1, which is 3r minus 1, and my r is t plus 1. Observe that t is an integer, 1 is an integer, the sum of two integers is an integer, so legitimately that is an integer. But that simply means that x is an element in C, and that simply means that D is a subset of C. C is subset in D, and D is subset in C, would imply that C equals D. And we're done. Subsection 1.1.6, proper subset. If A and B are sets, then A is a proper subset of B if and only if A is a subset of B, but equality is denied. Interesting. Let me give you a quick example. Let A be the set of all integers such that x equals 4k, k in Z, so multiples of 4. And let B be the set of all integers such that x equals 2k, multiples of 2. Even numbers. The question is to prove that A is a proper subset of B. Proof. Hint. Show that A is a subset of B show that A is a subset of B, and then find an element x in B such that x is not an element in A. Details of the proof, I leave that as a sieves. That is something you'd see throughout my lectures in abstract algebra. SEFSS. I'm not sure how you want to pronounce that. You could call it SEVS or SAVES or whatever, but it simply means that exercise is left as a simple exercise for serious students. SEVS, simple exercise for serious students. So our last little exercise in the first part of sets is a sieves. So go ahead and play with that. And for those of you taking this class with me, I would expect you to show me this proof in class. Stay tuned for part 2 of our lecture on sets. Thank you.